guys, welcome to Wong Chemistry channel. For this video, we'll discuss about the illustration for the formation of Lyman series, Balmer series, Paschen series, Brackett series, and last but not least, Pfund series. So we'll focus on the formation of all these series. Before we go into the formation of the Pfund series, let's look at the relationship between Bohr atomic model and also the energy level diagram. We'll be using this energy level diagram a lot in this video. So what is the relationship between Bohr atomic model and energy level diagram? Simple. They are actually the same. Alright, your Bohr atomic model and your energy level diagram is actually the same. The energy level diagram is actually the simplified version of your Bohr atomic model. It's basically cutting through your Bohr atomic model to half. So that is your nucleus. So you can imagine in your energy level diagram, this is your nucleus. This is where the nucleus is located. Okay? So you can see you're starting off with your n equals to 1 over here. That is your n equals to 1. So that is your n equals to 1. This line actually represents n equals to 1. And then you have your n equals to 2. So this line represents n equals to 2. So you have your n equals to 2 energy level. Alright, your shell n equals to 3. So you have your n equals to 3. Your n equals to 4. You can see that. That is your n equals to 4. And then you have your n equals to 5. That is your n equals to 5. And so on until infinity. Depends on your question. Depends on how many energy level do you need. Alright. So this is the relationship between the Bohr atomic model and energy level diagram. Why are we using energy level diagram? Because it's easier to draw. Imagine drawing your Bohr atomic model and also your energy level diagram. Which one is easier? Obviously your energy level diagram because it's only lines. Alright? And you can show the same thing. Like I want the electron to drop from n equals to 4 drop to n equals to 2. So you can have your electron at n equals to 4 drop all the way to n equals to 2. So that is still showing the transition where the electron drop from n equals to 4 to n equals to 2. Okay? So that is how we use the energy level diagram. We'll be using this energy level diagram a lot. Just want to show you that your Bohr atomic model and energy level diagram actually represent the same thing. Okay? So how do we draw the energy level diagram? We always start with the axis of y. The axis of y is actually the energy, represent your energy level of or shell or orbit. So it's your n1, n2, n3, n4, and n5. No matter what, whether we are using it or we are not using it, your energy level diagram must always start with n equals to 1, even though we are not using it. Whenever you want to draw your energy level diagram, you must always start with n equals to 1 and then just a straight line. And then you have your n equals to 2 follow up there. And then you have your n equals to 3 up there. That is your n equals to 3. I want to point out something that you might not realize but it's actually quite obvious. Is the gap between the energy level. Look at the gap between this energy level and this energy level. Alright, you realize that the gap gets smaller and it's a must over here for the gap to get smaller. Look at my n equals to 4. The n equals to 4 and the n equals to 3, look at the gap. The gap also become smaller. Alright, so the gap between each energy level going up to another energy level, going up to another energy level, the gap must get smaller. It's not needed to measure how much smaller as long as your eyes can see the difference, alright? It's important for you to clearly see that the gap becomes smaller. There you go, your n equals to 5. And you can see over here, the gap again becomes smaller. N equals to 6, gap becomes even smaller. N equals to 7, significant that the gap becomes a lot smaller. So make sure when you draw your energy level diagram, you must have the gap smaller. Alright, the gap between each energy level when you move up, the gap must be significantly smaller. So the question will be, I say we must always start with your n equals to 1. You must start with your n equals to 1 no matter you're using it or not. So the question will be, when do we stop? Alright? Do I draw until n equals to 7? Do I draw until n equals to 8 only? No, depends on the question. If the question only mentioned about the transition until n equals to 5, then you can stop at n equals to 5. Okay? If the question mentioned about n equals to 9, then you need to go all the way up until n equals to 9. Okay? So it always depends on the question, how many energy level that you must have. But no matter what, no matter you are using it or not, your energy level diagram must always start with your n equals to 1. Because without n equals to 1, you wouldn't have n equals to 2, you wouldn't have n equals to 3. So you must start with n equals to 1, and also the gap must become smaller. Alright, that is the tip to draw an energy level diagram. So, before we talk about the formation of Lyman, Balmer, Paschen, Brackett, and Pfund series, make sure you know the formation of line spectrum of hydrogen atom. There is a video that I discussed about the formation of line spectrum of hydrogen atom. So, if you haven't watched the video, make sure you watch the video first, okay? So, we will actually focus on your step 4, step 5, and step 6 over here to show the formation of every series. So, let's recall back what is actually your step 4 and step 5 and 6 mentioned. So your step 4 stated that the electron at the higher energy level, which is your excited state, is very unstable. So let's say I have an electron at n equals to 3. I know that the electron at n equals to 3, let's say, is at the excited state. The electron then need to drop back to a lower energy level and emit light in the form of photon. So, the electron need to drop to a lower energy level. So, let's say my electron at n equals to 3 drop to n equals to 2. And during this process, light being produced, alright? And everybody knows that this light will have a specific wavelength. And this specific wavelength will then go through a slit, and then a prism, and then it will form a line in your line spectrum. Okay, so you form a line in your line spectrum. Alright, so I hope this recall about the formation of line spectrum. So let's say another electron at n equals to 6. So n equals to 6, and then my electron drop all the way down to n equals to 3. Okay, so again, light produced. When light produced over here, this light will have a specific wavelength. And this specific wavelength will then drop on the line spectrum. Okay? Makes sense? That is how the line spectrum is being formed. I hope you remember this, okay? So right now, the two examples that I give to you is the electron from n equals to 3 drop to n equals to 2. Alright? Another example is your n equals to 6 drop all the way to n equals to 3. Okay? And the formation of every series depends on the electron dropping to which energy level. So if I have all the electron right now drop to n equals to 2, no matter from where, but it's all going down to n equals to 2, then this group of transition will be located in the same series. Okay? Same thing over here. If everything that I have right now drop to n equals to 3, you have 6 going down to 3. You can have 5 going down to 3. You can have 4 going down to 3. Right? But can you have 2 going down to 3? No, right? 2 must be going up to 3. So all this again will be in the same series. So in the other words, how is actually Lyman, Balmer, Paschen, Brackett, and Pfund series being formed? Easy. All the electrons must drop to the same energy level. Let's go into that. So, for every series, you need to know 3 things. The name of the series, the final energy level, the electron dropping to which energy level, and also the region. So, the first one is your Lyman series. Lyman series is produced when all the electrons drop to n equals to 1. So your n final right now is 1. In the other words, you are moving from 2 to 1. You are moving from 3 to 1. You are moving from 4 to 1. All the electron is dropping to n equals to 1. That will be your Lyman series. And all the lights that produced in Lyman series were dropped within the ultraviolet region. All the lights that produced will have a wavelength within the ultraviolet region. Next is your Balmer series. Balmer series, your n final must be n equals to 2. In other words, all electrons must drop to n equals to 2. You can have 3 to 2, you can have 4 to 2, you can have 5 to 2, and so on. Okay? So everything must drop to n equals to 2, and during the transition, light will be produced. The wavelength of all the light will drop within the visible region. Visible region is the light that you can see, is the color that you can see. Your red, blue, yellow, green, purple, all that is within visible region. Next is your Paschen series. Paschen series, n final is n equals to 3. Same thing, all electrons must drop to n equals to 3. You can have 4 dropping to 3. So since 3 is your final, you must at least drop from n equals to 4. Okay? You cannot drop from n equals to 1. 1 cannot drop to 3. You get what I mean? So you must drop from a higher energy level to a lower energy level. And the lower that you are going for is 3. So 4 to 3, 5 to 3, and so on. And during this transition, all the lights that produce will have a wavelength within infrared region. Simple. Next, we have Brackett series. Check the spelling. Alright, your Brackett series over here is your n final equals to 4. In other words, you can have electron from 5 drop to 4, 6 drop to 4, and so on. And during this transition, all the light that produced will fall within infrared region. Last but not least, Pfund series, your n final must be 5, and all the light will drop within infrared region also. We'll go through one by one of this series, don't worry. Just before we go on, make sure the spelling for all the series must be correct. You must be able to write the name of the series correctly, okay? Let's start off with the Lyman series. We know that the Lyman series, n final must be 1. Therefore, your n initial can be 2, 3, 4, 5, 6, and so on. Alright? So this is the energy level diagram that I'm looking at. Since we are going for Lyman series, means that all the electrons must drop to n equals to 1. Look at my energy level diagram. The gap between the energy level must get smaller. Okay? So the first line in the Lyman series must be n equals to 2, drop to n equals to 1 and produce the first line. Okay? So this is what we call first line of Lyman series. Okay? First line of Lyman series must be n equals to 2, drop to n equals to 1. Okay? The second line will then be, obviously, n equals to 3, drop all the way to n equals to 1 and form the second line. So that is the second line. Then the third line will be definitely from n equals to 4, drop all the way to n equals to 1, forming the third line. And the fourth line will be from the n equals to 5 over here, drop to n equals to 1, and that is the fourth line of Lyman series. Then the fifth line will be n equals to 6, drop all the way to n equals to 1. That is the fifth line. Okay? And then you can have the next line will be from n equals to 7, drop all the way to 1, forming the sixth line. The next transition can be from the n equals to 8, drop all the way to n equals to 1, and then you form another line in the line spectrum. Bear that in mind, every time when the electron drop, you produce a light. And every time this light produce a wavelength. Alright, this is the symbol of wavelength. So every single time it produces a light and a specific wavelength. Okay? And all this wavelength will then be on the line spectrum. If you have another line over here, then this transition will be from n equals to 9 drop to n equals to 1. And to ensure that this is Lyman series, everything must drop to n equals to 1. Okay? And the first line of the Lyman series must be your n equals to 2, drop all the way to n equals to 1. That is the first line that you will form in the line spectrum of Lyman series. Make sense? And we agree that during every transition, there will be a light that produced, and the light will have a specific wavelength. And all this wavelength, the entire wavelength, will be dropped into the same region. And the region of Lyman series is ultraviolet. Means all the wavelength will be located in this ultraviolet region. And since it's an ultraviolet, it wouldn't be orange, turquoise, purple, green color. It's not that color. This color is just to show you the transition. The ultraviolet color will be ultraviolet. Okay, like your bluish purple, that will be the color of your ultraviolet. So the first line until the last line will be holding the same color of ultraviolet. And all that will be in this same region of wavelength. Make sense? So there are still a few things that we want to look at this Lyman series line spectrum. Just a kind reminder over here, line spectrum is not necessarily reading from the left to the right. There is a way to identify which is the first line of Lyman series. Okay? It's the gap. Looking at the gap on the left hand side and the gap on the right hand side. Okay? Obviously, the biggest gap represents where it starts. Okay? So this obviously is the first line of Lyman series. Okay? Since we know that this is the first line, therefore we know that for this Lyman series line spectrum, we'll be reading from the left to the right. Whenever it's a first line of Lyman series, therefore, the first line transition must be your n equals to 2 to n equals to 1. Because n final for Lyman series is 1. So the first line means n equals to 2 drop to n equals to 1. Okay? Next thing that we want to look at is the delta E. Delta E is the changes of energy over here. Alright? We know that every energy level having their own energy. Alright, they have a fixed amount of energy over here. So looking at this transition from where the electron at n equals to 2 drop to n equals to 1, the changes of the energy is very small compared to you have electron at n equals to 8 drop all the way to n equals to 1. Look at the energy changes. The delta E over here is huge. Okay, there is a lot of energy being released. You are dropping all the way from n equals to 8, drop all the way down to n equals to 1. So the energy that you release, the energy change is a lot. In the other words, the first line, delta E, is very low. The last line of delta E is extremely high. Therefore, moving from the left to the right, the delta E actually increases. Okay? Since the delta E right now increases, what happened to the frequency? Frequency over here is your mu. This is your frequency. So the frequency will also increase because they are directly proportional. Delta E equals to H mu. When the delta E increase, frequency increase. How about wavelength? When the frequency right now also increase, alright? Frequency equals to speed of light over lambda. Lambda is the wavelength. Okay? So when the frequency increase, the lambda actually decrease. The wavelength actually decrease. Okay? Because they are inversely proportional. As a conclusion, moving from the first line to the last line over here, the delta E will increase, the frequency will increase, but the wavelength will decrease. Okay? Simple? Easy. So next, let's look at Balmer series. So Balmer series, your n final over here must be n equals to 2. In the other words, all electrons must drop to n equals to 2. Since everything must drop to n equals to 2, the initial must be higher than 2. The initial will be 3, 4, 5 and so on. Must be higher than 2. And you will actually realize that in Balmer series, your n equals to 1 over here will not be used because we will only stop at n equals to 2. So even though n equals to 1 is not used, but in the energy level diagram, your n equals to 1 must be that. Alright? Always remember your energy level diagram, you must start with your n equals to 1. So the first transition in the Balmer series will be your n equals to 3 drop to n equals to 2. And that will give rise to the first line in Balmer series. Okay? The first line in Balmer series must be your n equals to 3 drop to n equals to 2. That is the first line. How about the second line? The second line obviously is from your n equals to 4 to your n equals to 2. That is the second line in your Balmer series. How about the third line? Going up again. From the n equals to 5, drop all the way to n equals to 2. That will be the third line in Balmer series. Where do you think the fourth line come from? Obviously, the fourth line will be produced because the electron drop from n equals to 6 to n equals to 2. That will produce the fourth line in the Balmer series. The fifth line will then from the n equals to 7 all the way down to n equals to 2. That will be the fifth line. And then in my example, you have the sixth line only because we stop at n equals to 8. So the sixth line over here will be from the n equals to 8 all the way down to n equals to 2. I don't know whether you realize or not, but since we agree that it's a Balmer series where the n final must be n equals to 2, you realize that everything dropped to n equals to 2. That is the Balmer series. And we know that during every of these transition, we will produce light that have a specific wavelength. Alright? Every transition that you form over here will produce a light, a packet of light, a photon that carry a specific wavelength. And all this wavelength will drop into one region, and the region for Balmer series is visible region. This is the region that the Balmer series were located. Okay? So all this wavelength that you have in this line spectrum will be in this region. Okay? It won't be out of that visible region. It will just be in that frame of the visible region. All that wavelength, no matter you are from 8 to 2, 7 to 2, 6 to 2, 5 to 2, it doesn't matter. But all the wavelength that you produce will definitely drop into that particular region. Okay? So we are still under Balmer series. Let's say I told you that this is the line spectrum of Balmer series. Just giving you this line spectrum without the energy level diagram. So first and foremost, you need to understand the line spectrum by identifying who is the first line in that line spectrum. And the method is very simple, looking at the gap. So the gap on the left is largest compared to the gap that you have on the right. So obviously, we will start reading from the left to the right. Start reading from the left to the right also means that this is the first line of the Balmer series. First line of the Balmer series means what? Means you will form this line when the electron from n equals to 3 drop to n equals to 2. Then you produce this line. Why n equals to 2? Because it's the Balmer series. Balmer series, n final is 2. So the first line in the Balmer series must be from 3 all the way to 2. So the second line over here will be n equals to 4 drop to n equals to 2. The third line of Balmer series will be n equals to 5 drop to n equals to 2. See that? So that is how we read the line spectrum of Balmer series. And this is for the fourth line, the transition that produces the fourth line, and the transition that produces the fifth line will be n equals to 7 drop to n equals to 2. The sixth line will be the transition from n equals to 8, drop all the way to n equals to 2. Okay? Next, look at the delta E. Look at the energy changes. We know that the energy changes for the first line is only the changes between energy level 3 and energy level 2. So the delta E, the energy changes is very low. Compared to the last line that I have, the sixth line over here, the delta E must be extremely high. Why? Because the changes is from n equals to 2 and n equals to 8. All the way from n equals to 8, energy level at 8, all the way down to n equals to 2. So the energy difference is very huge. Therefore, moving from the first line to the last line, the delta E over here increase. Okay? And when the delta E increase, what happened to the frequency? The frequency also increase. When the frequency increase, what happened to the lambda? The wavelength decrease. Everything is the same as just now. Okay? What most important is you must be able to identify who is the first line. Okay? By only looking at one thing, the gap between the lines. The biggest the gap, that is the first line. Okay? Therefore, I hope you realize that the gap between each line will actually become closer as well. Look at the gap. The gap between every line will actually become closer also. See that? So obviously, the blank area in the line spectrum also get smaller. Okay? Simple. So next, let's look at Paschen series. Paschen series means n final must be n equals to 3. In the other words, all the electron must drop to n equals to 3. Therefore, your n initial, the electron must drop from a higher energy level than n equals to 3, starting from 4, 5, 6, and so on. Okay? And the first line of the Paschen series obviously is your n equals to 4 drop to n equals to 3. That is the first line in your Paschen series. Next, you have your n equals to 5 to n equals to 3. Then you have your n equals to 6 to your n equals to 3. The fourth line will be your n equals to 7 to n equals to 3. The fifth line of Paschen series will be your n equals to 8, drop all the way to n equals to 3. As we have agreed, the final energy level of Paschen series must be n equals to 3. Therefore, you can see that all the electron is dropping back to n equals to 3. You must drop to n equals to 3. The first line over here must be the one that from the closest energy level. Okay? Closest n. Therefore, the first line must be from the n equals to 4, drop to n equals to 3. Always remember that. The first line is always the closest energy level. Okay? And as always, everybody produce a light over here and the light will drop into one particular region. Alright, all the light will have a wavelength that drop into a particular region, and the region for Paschen series is infrared. Means that all the light that you produce from this transition will drop into this particular region of infrared. All the wavelength will be located in this region. Okay, your region of infrared. So you will have the wavelength located in this area. Okay, that is your Paschen series. Infrared will have no color. So we cannot see infrared color with our bare eyes. Therefore, line spectrum of your Paschen series should be just black. Alright, should be just black. We cannot see the color, to be honest. Alright. So this is the formation of the line spectrum of Paschen series. Okay. So slightly different from the previous line spectrum. This line spectrum of Paschen series given is this. Okay. So from this line spectrum, you need to first identify the first line is from the left or from the right. Simple. We'll look at the gap between the line spectrum. So the gap over here is the largest. Since the gap over here is the largest, therefore, this must be the first line of your Paschen series. Okay? And the transition to produce this first line must be n equals to 4 drop to n equals to 3. Why? Because the n final for your Paschen series must be 3. So the first line in the line spectrum must be from the n equals to 4 drop all the way to n equals to 3. While for the second line in this series will be from the n equals to 5 drop to n equals to 3. The third line will then be n equals to 6 drop to n equals to 3. Okay? Make sense? Simple. The fourth line will then be from the n equals to 7 drop all the way to n equals to 3. That is my fifth line, and the fifth line will be from the n equals to 8 drop to n equals to 3 and so on. The sixth line over here will be from n equals to 9 drop to n equals to 3. Okay, for sure everybody drop to n equals to 3 because it's a Paschen series. Okay, simple. That is how we read the line spectrum for a particular series. You must know the n final. You must identify who is the first line. So as always, we are going to find the relationship between the delta E, the frequency, and the wavelength. And in this case, will be slightly different because we are reading it from the right to the left. Why we are reading from the right to the left? Because the first line right now is on the right hand side. Okay, so we are reading from the first line to the last line, knowing that the delta E of the first line is extremely low. Moving to the delta E of the last line will be extremely high because of the energy difference. For the first line, it's only n equals to 4 to n equals to 3. And then all the way down, the energy level gap become bigger, bigger, and bigger. Therefore, the delta E over here will increase. And as always, guys, when delta E increase, frequency also increase. When frequency increase, wavelength decrease. Okay? Simple. Since everything is the same, so right now I want to introduce something new into this line spectrum. Okay? So let's look at the blank area. Everybody knows that the blank area between the line in the line spectrum shall get smaller. So you realize that the blank area right now becomes smaller and smaller. In the other words, the line in the line spectrum become closer and closer. So there will be a point where all the line in the line spectrum become too close to each other and you cannot differentiate which line belong to which transition. Look at it. So there is a black whole thing over there because all the differences is too small, and that is what we call continuum limit. Alright, that is what we call continuum limit. And this continuum limit is actually proof that the differences between the energy level becomes smaller when you move away from the nucleus. The further you are from the nucleus, the closer the energy level difference, the smaller the gap. Okay? And there will be a point where the energy level differences are so small that they are actually like sitting on top of each other without any blank area. And that is what we call continuum limit. Okay? It's a limit where we cannot differentiate the transition anymore. Okay? Next, let's look at Brackett series. Alright, it's already the fourth series, so by right you should be extremely good already. And the only difference is, in the Brackett series, your n final is n equals to 4 over here. Therefore, your n initial must be all the energy level above n equals to 4, which is n5, n6, n7, and above. Okay? And the first line in your Brackett series must be from your n equals to 5 all the way down to your n equals to 4, and that will be the first line in your Brackett series. Second line in your Brackett series will be from your n equals to 6 drop to n equals to 4. Moving to your third line of the Brackett series, electron at n equals to 7 drop to n equals to 4. That is the third line of the Brackett series. the fault line of the Brackett series will be N8 to your N4. Let's say if I have another line over here. Alright, so this line will be from what energy level to what energy level? Obviously, this will be from the N equals to 9 drop to N equals to 4 because it's the fifth line. So the fifth line will definitely from a higher energy level than the fourth line, which is N equals to 9 drop to N equals to 4. So all this transition will again give out a light, and all the light that produced will drop within the region of infrared also. Okay, so all the light will again drop in the range of infrared over here for the Brackett series. Okay, same as before, infrared means you have no color that we can see with our eyes. All the lines that form in the line spectrum should be just black as it is. Okay, because it's an infrared region, we cannot see the color of infrared with our bare eyes. Okay. Next and also the last series that we will look at in our syllabus is your Pfund series. Pfund series, the only thing that makes different over here is your N final, where for the Pfund series, the N final is N equals to 5. Means everything must drop into N equals to 5. Therefore, the initial energy level for the Pfund series must be 6 and above. Okay. And the first line of the Pfund series will definitely from the N equals to 6 to N equals to 5. You can see over here, N equals to 6 to N equals to 5. And this will definitely be the first line in the Pfund series line spectrum. The second line will be N7 to N equals to 5. The third line will be N equal to 8 to N equal 5. Okay, that is the first, second, and also the third line. Alright. And all this will give out some light, and all the light will be then in the region of infrared. Okay, so you have your Paschen series, Brackett series, and also Pfund series all located in the same region of infrared. Okay, because infrared region is very large, alright, it's a big range over there. So all the three series light will drop in the same region. And as we agree, infrared region have no color, therefore all the lines that you will observe in the line spectrum will be black. Okay, so let's say I have another line over here, the fourth line of my Pfund series. So the fourth line will be N what dropping to where? Simple, it must drop to N equals to 5 because it's a Pfund series. So the first line is 6 to 5. 7 to 5 for the second line, 8 to 5 for the third line. How about the fourth line? Alright, the fourth line is definitely N equals to 9 to N equals to 5. Okay? Okay, if I'm having the fifth line in the lines in the Pfund series. Pfund series means N final must be 5. So you must drop from N equals to 10 to N equals to 5. Okay, it's simple. The number of line plus with the final energy level. The fifth line plus with the final is 5. Therefore, the initial must be 10. Alright, look at that. So that is the little trick to identify the transition that produce the lines in the line spectrum for a certain series. But you must make sure you know the N final is equals to 1. So the N final for Pfund series is N equals to 5. So you can work out the fourth line must be from N9 because 5 plus 4. The fifth line must be from N equals to 10 drop to N5 because 5 plus 5, 10. Okay, see that? Simple. So a bit of conclusion over here. When all the transition drop to N equals to 1, that will be your Lyman series. Lyman series means everything drop to N equals to 1. And all the transition were located in the ultraviolet region. Okay. Next, when everything dropped to N equals to 2, that is your Balmer series. Alright, we know that when everything dropped to N equals to 2, that is your Balmer series, where all the wavelength will be located in the visible region. Okay, the wavelength will be in the visible region. Next, when everything drops to n equals to 3, that is your Paschen series. And in this series, everything will drop in the infrared region. Okay, all the wavelength will drop into infrared region. Next, when all the transitions stop at n equals to 4, that is your Brackett series. Check the spelling, double T. So this Brackett series will produce lights that have the wavelength also within the infrared region. Okay. Last but not least, when all the electrons drop to n equals to 5 as the final energy level, that is your Pfund series. And in this Pfund series, all the light that produced will also again be the infrared region. Okay, so this is the conclusion and the summary of all the 5 series that you have. Just make sure you know that your Lyman series, your n final must be 1, Balmer series n final must be 2, Paschen series n final must be 3, your Brackett series n final must be 4, Pfund n final must be 5. Don't make any mistake on this, okay? And also make sure all the spelling is correct. Next summary is on how to read your line spectrum. We will always start reading the line spectrum from the biggest gap. So the biggest blank area over here is on the left hand side. In the other words, that is my first line. Since it's the first line, therefore we will be reading from the left to the right. Okay? And the first line will always have the energy lowest. Moving up, the energy will increase. Therefore, the first thing is your delta E increase. Okay? And your frequency will then increase because of the formula. Delta E increase, frequency increase. And the wavelength will decrease because of the formula also. Okay? In the next video, we'll talk about all this formula. So don't worry about the formula. You can check it out in the next video. While for the second line spectrum, the blank area biggest is on the right hand side. Therefore, you will be start reading from here. So let's say this is the line spectrum for your Lyman series. Lyman series means n final equals to 1. So this is the first line. First line means the transition that produced this line will be n equals to 2, drop to n equals to 1. While the second line over here is your n equals to 3, drop to n equals to 1. See that? Okay, so if it's a Lyman series, we don't know what series, that depends on the question. Alright? But most important, same thing, your delta E will increase, your frequency will increase, but your wavelength will decrease. Okay? So please be extremely careful on how you read your line spectrum. Always find the biggest blank area. We always start with the biggest blank area. The biggest blank area will give rise to the first line of the line spectrum. Make sense? Simple? Alright, let's try a few examples. So example 1 over here. Below is the line spectrum of Paschen series. Paschen series, guys, n final must be 3. That is the first thing that should come into your mind. State the transition of electrons that form line S and T. So my S and T is over here. That is my S, and the next one is your T. Okay. So first and foremost, when you come across a line spectrum, first thing, what do? You need to identify the first line. You need to identify we are reading from the left or we are reading it from the right. In this case, the biggest gap over here is on the right. Therefore, we will be reading from the right to the left. Okay? In the other words, this will be the first line of the Paschen series, second line, third line, fourth line, and also the fifth line. Okay? Simple. So there is some traditional way to do it. Knowing that first line in the Paschen series means n equals to 4, drop to n equals to 3. That is the traditional way. Okay? So you know that that is your n equals to 5, drop to n equals to 3. That is the traditional way. Therefore, your T means n equals to 6, drop all the way to n equals to 3. So for the T, means the electron drop from energy level n equals to 6 to n equals to 3. That is a traditional way. If I don't want to use the traditional way, simple. How do I know the S is from which energy level to which energy level? You can work it out by identifying the number of line and also knowing that the n final right now must be 3. So it's the 5th line in the Paschen series. Therefore, the n initial will be 8 because 3 plus 5. 3 plus 5 equals to 8. Therefore, the 5th line in the Paschen series must be from the n equals to 8 drop to n equals to 3. If you don't trust me, you can check with the traditional way. So, T is the 3rd line, n equals to 6, drop to n equals to 3. 3 plus 3, 6. 2 plus 3, 5. 1, first line, plus 3, 4. See that? Alright, so it's not necessary to count all the way from the beginning. As long as you know the n final of that series, and you know which line is that, and then you know that the S right now is the electron drops from n equals to 8 to n equals to 3. So please be careful with the line spectrum given by the question. The line spectrum is not always reading from the left to the right. It can be from the right to the left, depends on the blank area. Alright, simple. Let's look at the second example. So in this second example, the question asks you to indicate the line in the Balmer series that has the longest wavelength, the highest energy, and also the lowest frequency. Knowing that it's a Balmer series over here, Balmer series means n final equals to 2. Okay, looking at your line spectrum, guys, looking at your line spectrum given by the question, you'll know that the line spectrum right now will be reading from the left to the right. Why are we reading it from the left to the right? Because of the gap of the blank area. So the blank area having the largest blank area on the left. Therefore, A will be the first line. Okay, so your B will be the second line, your C will be the third line, and so on. Alright, so we know that the first line of the Balmer series means this is the transition where you have n equals to 3 drop to n equals to 2. This is your n equals to 4 drop to n equals to 2, n equals to 5 drop to n equals to 2, n equals to 6 drop to n equals to 2, and so on. Okay, this will make your life easier in case you don't remember which one having higher energy. It's not needed to memorize which one having higher energy, guys. Just work this out. Look at the energy level. The first line is between 3 and 2. Small gap. The last line, your line F over here, is between 8, all the way, 8 to 2. So the gap between 8 to 2 is larger. Therefore, delta E over here is higher. Okay, so delta E is increasing. Knowing that your delta E equals to H mu, frequency. Delta E increase means frequency increase. Therefore, frequency increase, right? We also know that frequency equals to C over lambda. So when the frequency increase, lambda decrease. So lambda decrease. Okay, moving from the left to the right, your energy will be higher, your frequency will be higher, your wavelength will be lower. So which one will have the longest wavelength? So longest wavelength means I want the higher wavelength, but I know that moving from the left to the right, the wavelength decrease. So the longest wavelength will be line A. Line A will have the longest wavelength, okay? Because it has the lowest energy. Delta E is the lowest, therefore the wavelength will be the highest. Which one will have the highest energy? Highest energy is definitely your line F. your F will have the highest energy because it's the difference between the n equals to 8 drop to n equals to 2. So the line F will have the highest energy difference. And last but not least, lowest frequency. Which one will have the lowest frequency? Knowing that when you move from the left to the right, okay, moving from the left to the right, the frequency increase. Means that the F will have a very high frequency. Therefore, the lowest frequency will be the A. A will have the lowest frequency. It's very simple as long as you memorize the formula. But it's not needed to memorize which one have the highest energy. You can just work it out. The most important thing right now is still able to read and understand your line spectrum. You need to know that your line spectrum is not a must to start from left to right. It can be the vice versa. The line spectrum will always start when the blank area is the largest. Sometimes it might not start with the first line, but we will always start reading from where the blank area is the largest. Okay? So that's it about this video, talking about the formation of the 5 series all the way from your Lyman series, Balmer series, Paschen, Brackett, and also Pfund series. And also some details about the line spectrum for every series. Okay? So I hope by now you are very clear with the formation of every series and also their respective region and final energy level. Okay? If you have any question about this topic, drop it in the comment below and I will get back to you as soon as I can. Make sure you like the video and subscribe to my channel, and I'll see you again in the next video. Thank you for watching.